This conference will now be recorded.
Hello, my name is Jonathan from Facebook. I'm here with my partner, Vedi, from Intel to give this presentation. Thanks for joining. Our topic is Xeon Scalable Processor, FSP and Coreboot status update. This presentation is a follow-up session of last September's presentation in OCP Regional Summit. We will go through Facebook Open System Firmware status update, and then give an overview of Intel Firmware Support Package, FSP. And then we will talk about the Coreboot Xeon SP FSP status and the Coreboot design. Then we will give summary and the next steps. And also, you will find another video is about the demo. I go to the first part, and Vedi will go through the second part of this presentation. In Facebook, this is the open system firmware status for server. For networking server, we have Minipack in production. It is based on Broadwell D. It is a one-socket server. In the meantime, we completed proof of concept on computer servers. On Monolith, which is a one-socket server based on Broadwell D, and the Tioga, which is a two-socket server based on Skylake SP. We are working together with Intel and our partners on bringing up OSF on Delta Lake, Sonora Pass, and Xeon computer servers. They have 1, 2, and 8 Cooper Lake SPs respectively. Here is a screenshot of Target OS running on Tioga Pass, which has Skylake SP processor. Here you can see that there are two sockets. Each socket has 18 cores. Each core has 2 threads. This is a screenshot of Target OS running on Yosemite v3 Delta Lake. Delta Lake is a server of the Yosemite v3 platform. You can see that it is only showing one CPU. That's because we are working on the bring up. The bring up is in progress. Now is the second part that Vedi will give the presentation. Thanks.
Thanks, Jonathan. So let me go through the Intel firmware support package overview, and then we'll click down on the server class functionality needed in the FSP firmware support package, and then we'll actually focus most of the presentation on the Coreboot side of the functionality and what we need to do to enable the Xeon class multi-socket OCP platforms. So the firmware support package essentially gives you 3 different attributes of initialization, which is processor, specifically for the multi-socket, that includes all the way up to 8-socket, chipset initialization, and the memory initialization that can be easily integrated with the bootloaders using the well-defined APIs. The FSP is actually distributed as a binary. You can actually use the APIs to integrate with the bootloader. You can customize the attributes that FSP exposes through the binary customization. And then FSP does not actually provide certain functionality that need to be incorporated in the Coreboot side of the implementation. This includes SMM functionality, ACPI tables, setting up the multi-socket ACPI tables like SRAT and so on, and then the advanced RAS functionality. Let's take a look at the FSP functionality needed for multi-socket Xeon scalable processors. You probably might have heard of, heard about the client-side firmware support package. So there are a few changes needed on the server side, server class Xeon scalable processors. Left-hand side gives you a 2-socket platform with Xeon Skylake SP CPUs. Each CPU has its own memory attached to each socket. And then you essentially have UPI that's actually connected between the two CPUs. And then you have each one of the sockets has its own PCIe controllers that are actually attached to. And then you have on the boot socket, you have chipset to connect to your ESP flash and the firmware and the boot drive and so on. First and foremost, for FSP support for the multi-socket Xeon scalable processors, you need a capability to do the multi-process initialization. So in this case, we have two sockets, socket 0 and socket 1. There is a selection protocol, CP protocol that essentially gets used to identify which one will be the SBSP core that will actually do the initialization. Then it has to get into the KTI initialization, which is essentially looking at both sockets, figuring out the socket topology and figuring out the optimal route and so on. Once that is done, the next step would be to do the memory initialization. So you have to go through the memory training to identify the DIMM type, connector type, capacity, the frequency, and so on. After that, you need to be able to do the integrated I/O initialization. There are two parts to it. One before the memory training, the other one is after the memory training. That includes going through the PCIe link training, figuring out the number of links and which devices are connected and so on. So is the case with the PCH initialization. So let's take a look at what extensions we need on the Coreboot side. Hopefully this gives you a flavor of what's needed on the FSP side. So on the Coreboot side, we need very similar functionality like we talked about, taking the client class FSP and delivering the server class multi-socket platform capability. We do need similar functionality on the Coreboot side. Because Xeon scalable processors run on single socket as well as multi-socket OCP platforms, we need to be able to enumerate number of sockets, number of cores that are actually available in each one of those sockets as the step one. That includes enumeration, includes the API IDs and so on, and then be able to actually configure each one of those threads with specific Xeon class MSRs to be able to control the turbo ratios and power, thermal, TDP limits, and so on. The next step in the initialization is the integrated I/O. On Xeon SP, the integrated I/O is split into multiple units, which are called stacks. Each stack sits on its own physical bus address range, and it has its own 32-bit memory space, 64-bit memory space for prefetchable and non-prefetchable windows. We need to actually use that as a way to configure the PCIe bars that are actually sitting behind each one of those stacks. So that is the second step. And then the third one is server class multi-socket platforms do require additional ACPI tables in Coreboot. Things like MADT and SRAT, SLIT, DMA support functionality need to be enabled through DMAR, for example. So there is quite a bit of ACPI NUMA table plumbing that we need to actually pay attention to. Then there is an advanced functionality that needs to be implemented. As I mentioned, FSP does not have SMM, RAS, and so on. So we need to be able to implement that functionality through Coreboot. Let's click down on the integrated I/O, what it looks like behind the scenes. So if you look at Skylake SP, Skylake SP has 6 stacks. The bottom 2, we do not use them in OCP platforms. The first stack is called CPU stack, where you have the CPU bridge, and then the next 3 are the PCIe root bridge, stacks, stack 0, P stack 0, 1, and 2. Behind each stack has its own bus-based range, and this picture does not include the MEM32 and 64-bit windows, which is also part of which needs to be partitioned for each one of those stacks. Certain uncore devices may actually sit on these stacks. That includes the PCIe stacks as well. And then you have IO stacks also sitting behind each one of these stacks. And the goal of Coreboot is to go do the enumeration behind each one of these physical buses. We use the existing Coreboot bus 0 enumeration capability, and we build on top of that by looking at different stacks through the hub that's available in Xeon FSP package, and then we enumerate all the PCIe devices behind that, and then we actually do the PCIe bar assignment based on which stack it belongs to. And then we actually go through the standard Coreboot step of reading and assigning enabling the resources. Let's take a look at the hub definition. This is one sample hub definition that we are using. Skylake FSP hub definition is the one that you are actually seeing on this slide. If you look at the right-hand side, IO base, IO limit. There is also IO APIC base and limit that we need to be using to configure the IO APIC windows. And then you have MEM32 base and 64 base, prefetchable and non-prefetchable, bar windows. And then you have bus base and bus limit at the top. So we use this information that is actually coming from the Skylake SP hub to enumerate the IIO stacks, enumerate all the devices behind each one of those IIO stacks, and then actually use the data that is available in the hub to restrict the windows for IO as well as memory windows, and then actually do the allocation. Let's take a look at what the PCIe device looks like behind each one of these stacks. So if you look at the device tree in Coreboot, you essentially see all the devices that are actually sitting on bus 0, and then you expand the enumeration capability on top of them. You will see devices actually sitting on different IIO stacks. For example, the Mellanox NIC is actually sitting on bus 2, and then if you look at the windows for that bus 2 behind in the right-hand corner, you can actually see it's a PCIe bridge. This is the root port 1A, and it has its own IO behind that bridge, and MEM32 behind that bridge, as well as a prefetchable memory behind that bridge. We need to be able to use this and configure it. That's exactly what the working solution is actually showing you on this slide. Let's take a look at some of the additional functionality. So every board will have its own bifurcation settings. It will have its own GPIO table, GPIO configuration, and then it will have its own IIO, the PCIe port configuration as well. Things like number of lanes, bifurcation rules, both for PCH and PCIe controller. We need to be able to provide that through the FSP UPD interface to be able to configure the devices correctly. In summary, we talked about firmware support package for Xeon scalable processor support. And you integrate into the bootloaders using APIs, handoff blocks, and UPD structures that we actually briefly share on how we managed to use that to successfully boot TiogaPass board. We plan to continue the work with Cooper Lake SP FSP package on Delta Lake Yosemite V3 board, one socket configuration. Currently that work is going on, and once we do the boot up and successfully boot one socket platform, we'll move on to the two socket platform. Here are the OCP platforms that we have used. This essentially gives you the summary of Skylake FSP work on the OCP platforms. So the TiogaPass two-socket server was used for Skylake FSP and the Coreboot changes to successfully boot the two-socket platform for the Skylake processor generation. and we will move on to the Cooper Lake CPU processor generation using Cooper Lake FSP on OCP Delta Lake Yosemite v3 socket server. Once we do the boot up successfully, we will move on to the 2-socket configuration, which is OCP Sonora Pass board. Okay, in summary, what we are looking for is help in contributing to the open source Coreboot, firmware functionality to enable Xeon class FSP integration and the functionality that is needed. So things like RAS functionality that does not currently exist, hot plug functionality, SMI capability. We are looking for your help in contributing the Coreboot function, feature set to enable the multi-socket Xeon server platforms. In parallel, it would be nice if we can actually try out Xeon SP FSP based open system firmware for your boards, and look for pilots and production deployments, ideally, to extend the broad reach of our work with Facebook on OCP platforms. You can find out more details on the project wiki, open system firmware project wiki, as well as you can tune into the mailing list to get next level of details on the Coreboot development for the FSP functionality. We'll have a demo as a separate downloadable audio, the content. Feel free to actually click on the demo link to actually look at how the boot functionality works. The backup slides have a lot of details on the white papers. For more details, refer to these white papers. Thank you. Appreciate your time.
This conference will now be recorded.
You cannot hear me. Okay. Hello. Okay. Cool. Thanks everybody. Unfortunately, Reddy's audio doesn't work, but please ask questions through the question and answers tab, and ask the questions. Okay, thank you, John and Ron. I can to confirm that you can hear me. So I have not got any questions yet. Oh, there are questions. Do you have a doc on how to do this with stuff like? At this moment, we don't have doc. We are upstreaming. We actually already upstreamed the Tioga Pass Coreboot code to Coreboot, and it was merged. So that was for the Skylake SP generation. So that's the second generation of Xeon SP processor. For the third generation of Xeon SP processor, we have the code being upstreamed. So the code is in the public, and feel free to ask us questions. We are on it. We do plan to make a doc. But the priority is lower of doing that. We want to get the code sorted first to some extent, and then we start working on the doc. So the second question is also from Ron. I suppose that means where to buy this board. So today you can buy a Tioga Pass board from Win-Win. So it's an off-the-shelf board you can buy in a unit of one and plug into wall power. You can get Coreboot from the Coreboot community. you can get Linux boot because it's preloaded with a board from WinWin. The problem is FSP binary. So the Skylake SP FSP binary is a POC binary, so it's not available to the public. On the other hand, the current generation Xeon SP processor FSP will be made public after the processor gets mass production. Exactly when Intel will decide it, but it will be available. So at that time, you will be able to buy a hardware, and you will get Coreboot code from the internet, and you will be able to get FSP binary from Intel, which will be public, and you have the entire solution to customize. Any other questions? Let me go back to the chat window. IPMI stuff. IPMI stuff. Oh, there's a question about IPMI stuff. Yeah, we implemented IPMI in Coreboot and in Linux boot. You can see the code done for Tiocapass and for the Coreboot SP based platform in the public. How are training? You can also watch the other video, the other presentation that WinWin and I did for the server feature development, for some details about the server features. How the training failures reported. Okay, that's a good question. So FSP 2.1 has a new feature that errors during the FSP execution will be reported through FSP error blob. So the bootloader should pick up the data and report it. Another question, if Coreboot supports ACPI, yes, it does. So today, the Coreboot code for Skylake already generates tons of ACPI tables, including NUMA tables, SROD, SNIT, and DMAR tables, things like that. Where does OS receive the ACPI info? Yes, ACPI info is passed on to Linux boot the traditional way, and the Linux boot passes it on to the target OS kernel. In which part Coreboot receives the info? So Coreboot will receive some of the data from the FSP hubs, and the other data Coreboot will discover it. Then Coreboot assembles the ACPI table and pass it on to the later stage of the bootloader. Will the Sonora path support ASLEC SP? No. No. It supports Coreboot SP. Is a short link. Okay. Actually, I just saw the YV3 presentation, and this YV3 design is supposed to be modular in terms of the CPU socket. So if a different generation of SoCs are pin compatible, they could probably just change in easily. Let me go back to the question and answers window. Okay, so is FSP open sourced? This is an Intel question. Since Intel prioritizes ASLIC 2-socket over Cooper Lake, are there plans to use ASLIC SP on Sonora Pass? I'm not aware of such plan. Our focus is our company needs. So at this moment, Facebook's focus is on Cooper Lake SP. Ron asked, did I miss the timeline? No, you didn't. The timeline we are working on it, but the timeline is, at this moment is not. We cannot say it in the public. In Ajax session, in the Q&A session, he elaborated on this point in great detail. Question number 6. At boot time, does the BSP processor X, would it be possible to let all processors execute part of the firmware after they are ready to do so? That question was discussed in length in the chat window already. So there are a lot of good answers in the chat window. Please look at the chat window. One of the advantages of Linux boot is that as soon as Linux boot starts to run, because in this case Linux is on the flash, is actually part of the firmware. So at that stage, all processors runs tasks. Is there any utility allowed to check config file? I suppose is talk about FSP config. Intel has utilities. You can look at the static. You can look at the FSP image and configure it. And in the meantime, the bootloader, like Coreboot, can change the UPD settings before it runs before it executes the FSP modules like FSPM or FSPT during the boot time. Any other questions? Okay. Thank you everybody for joining the session. So you're welcome to join the virtual experience lab, and there's videos about booting Tioga Pass and booting Virus 3. And I will be there. Thank you. Bye.